but because I know you have missed a lot, that is totally fine. But I'll try to catch you up. But I'd rather do that than jump ahead to unsafe, just because
Yes, unsafe, man.
unsafe is a whole different topic. Unsafe is kind of simpler. We've already talked about it a little bit. I would highly recommend that bit, but I can at least mention these things. Let me just bring up what I want to bring up, though. What's going on?
The unsafe bit, or?
Yeah, I do.
Oh, really?
Yeah. I mean the bit of the book, but I'm not covering it. Um.
In
Uh.
Rust, in Rust, can you make an operation that recasted a homogeneous struct? Like, let's say a struct of all doubles with like a square bracket when it's just like when you just move into that specific field, it's not gonna let you do it, right?
Wait, can you
Like,
so if I have a
essentially-
struct of like 4 ints and you want to reinterpret it as an array of ints
Yes.
or a tuple of ints?
Like a tuple array or whatever.
All right.
I don't think Rust lets you do that. Because
I
have to use
think-
reinterpret cast in C++. So you should not be using reinterpret cast if you don't know what you're doing.
You definitely shouldn't be doing it if you don't know what you're doing.
But
I think there's a way. I think there's a way, but you probably have to hide it in some way. There's not really a safe way to do that. There's not like yeah. But you could build an unsafe abstraction, but if you can't have a situation where you have two I don't think you can have a situation where you have two references to the same thing through different types in Rust. Maybe you can, but you definitely can't have two mutable references to the same thing. As soon as you have two mutable references to the same thing, that's undefined behavior in Rust. But that is specifically about ampermute. We will be talking about how to safely have references through which one can mutate to the same thing. It's just a mess. Let's see. So first, one of the things you missed most of, but Dima did not, is in the pins. We talked an awful lot about RC. So RC is reference counted. It's a lot like shared pointer, except in shared PDR and C++. How it works is they all share, like all RCs to the same place. We don't really have multiple RCs to the same place here. Oh, I guess we do sort of here. Yeah, this is as a reference counter too. This is a singly linked list, right? So we have the RC of a node, and this is the node, but the thing pointed to also has this reference count in front. That gets incremented whenever you clone the reference using .clone. So .clone on an RC doesn't clone everything under it. It only clones the reference and bumps the reference count. And then the reference gets decremented whenever you drop the RC. A lot like shared pointer. The big difference between this and shared pointer, and this is a whole page in the Rust book, but I think we can understand it more quickly than that. Actually, let me go to this just quickly. The one difference is shared pointers are, I think, safe to, yeah, they're safe to share between threads. That is, you can have two shared pointers to the same thing between threads. And now, whether it's safe to share the underlying thing is a question in C++, right? And is not statically enforced by anything. But having two shared pointers to the same thing is safe. Do you know how that works? Do you know? I'm looking at you just because you know how it's shared pointer. Is there anything extra we have to do just because we can share them between threads?
Anything extra? I mean, you can add like
Like an atomic reference or something.
You could add it there. A mutex would be.
I like
Yeah.
the mesh like fitting.
Okay. So to be clear, I mean I don't mean sharing one shared pointer. I mean having two shared pointers to the same allocation, right? So the problem, or the thing that C++ has to do because of this, is it has to make all those operations that modify the counter atomic. It could have done that with a mutex around them, but they're actually just a single, integer. So what that means is when we increment, when one thread clones, it has to atomically increment. Because if it didn't atomically increment, it could do the classic multi-threading problem thing of, I don't know, it's classic to me, but where you fetch the value and then someone else fetches the value and then you both increment and then you both write back and only one increment happened, but two should have happened, Does that make sense?
Like a race condition?
Yeah, but that specific kind of race condition where you're where the problem is that increment is three things. It's
Yeah.
read, modify, write. But if you had an atomic operation,
Then that wouldn't happen.
then that wouldn't happen because it's effectively a mutex at the CPU level. It's just there's an instruction that just does that. Okay, but the yeah, so RC doesn't do that because if you're not sharing between if you're not sharing the underlying thing between threads, that's just expensive. But ARC, which is atomic reference counted, does do that. So Rust actually models, and I'm skipping past this intentionally, but I'd recommend reading it if you're curious. This talks about it. Rust models what is valid to be shared between threads with two traits, send and sync. They are yet again kind of fancy. These are actually, hello, please join us. These are yet again kind of fancy. These are yet another kind of trait. They're actually auto traits. They automatically get implemented if all of your constituent elements implement them. And I'm not going to get into them too much, but this is the way that Rust understands the difference between just having multiple mutable having multiple shared references to something and being able to share them over threads. That's sync. So ARC, the difference between ARC and RC is actually that ARC is send. You can, no, is that true? Yes. Yeah. ARC is send. ARC is atomic reference counted. Wait, do you have a question?
I was just wondering if it was like only send if the thing inside is sync.
Yeah, you're right. Okay, we'll get to that. But yeah, so ARC is send. RC is not send. RC, if you start with an RC on one thread, you can't send it to another thread. Because then they would have a pointer to something where there might still be an RC on your thread, and the modifications to the counter are not atomic, so the counter might end up screwed up, right? But ARC is send. But there's also sync. Sync is actually the second one to explain. A type of sync if it's safe to share between multiple threads. That is, if T is sync, amper T is send. So amper T, so far, we have only talked logically about amper T meaning being able to observe something, not being able to change it, right? Amper T is shared references, but we sometimes also call them immutable references. But they're only immutable by default. Sometimes amper T can let you modify the thing inside. But what's key here is that if T is sync, so T is probably sync, right, by default. But if you do something funny with pointers, then I don't think it's sync by default, and you would have to declare it as sync. I'm not getting into that, but some stuff in the standard library is sync.
Sorry, what is T?
T is just a type parameter. We're just talking about the abstract type T. But if T is sync, then amper T is send. Normally you'd think amper T, if amper T only observed, if amper T was like an amper I32 or something like that, then obviously it's send. I can send you a reference to something that I own as long as it lives long enough, right? But this isn't about living long enough. This is it valid for you to have this? And the only case where it might not be valid, really, is if having amper T actually lets you modify something. So far we haven't seen amper T let you modify something, but we have seen the ability to share memory. Share memory and modify it. Do you know where we've seen it? We just saw it. So we haven't seen amper t be something you can modify through, but we saw something that's very similar that you can modify through. But you don't really, it's like such a good abstraction that it might be sort of hidden that we're even modifying it. It's RC. If you have RC and you duplicate it, then you modified a shared reference count. Just the count though, right? RC does not allow you, and neither does ARC, allow you to modify this. Because RC says, effectively, for the type within RC, RC has the same rules as a shared reference. Which means you can't modify the thing inside it, right? But there's another type that I'll be talking about that does let you modify the thing inside it. Does that sort of make sense? Are you following so far? Okay. So who here has heard of RefCell? RefCell doesn't really have an analog in any other language that I know of. I thought of an example that did have a analog, but has anyone heard of RefCell? You've heard of RefCell. Okay. What is RefCell in your words? Don't worry about it.
Kicks the borrow checker to runtime, kind of.
Yes. So the borrow checker does, I guess it loosely you can think of it as doing two jobs. Make sure that every reference is alive, statically, right? So or every reference is to an alive object, right? Or a live thing, right? That's the lifetime bit. Or that's part of the lifetime bit. RC fixes that by kicking it to runtime, right? The borrow checker at compile time makes sure that we statically know that based on the shape of the stack, this reference will always be valid, right? Or this type will always be valid. I think our iter also had a lifetime parameter. Do you remember that at all? Sam, are you paying attention?
Sorry. Yeah, I don't actually remember it. My bad.
Okay. But yeah, so our iter, our iter had a lifetime parameter, right? Which meant that our iter couldn't live longer than our underlying list. Because that iter held a reference into the list, right? So the borrow checker does all that statically. It doesn't have any runtime cost. It just makes sure compile time, right? RC punts that to runtime. RC says, okay, I'm figuring that out at runtime with reference counts, right? The other part of what the borrow checker does is make sure to enforce the mutable XOR shared rule. Either it's mutable or it's shared, right? And this is an incredibly powerful rule because it makes it easier to reason about your code. It also makes your code easier to optimize. But the key thing is it makes it easier to reason about your code. If you can modify something, no one else can. And if you are looking at something, no one else can modify it. In fact, no one can modify it. Except sometimes that's just not enough. Sometimes we need to be able to share some data. But what would be nice is if it weren't an all or nothing thing, right? You could have a situation where you can share some data. You could pick between like the default of if you share data, you can't modify it. No one can modify it. Or if you share data, everyone can modify it, right? Those are two kind of opposite sides of the spectrum. RefCell actually lives in the middle. RefCell says, we will figure out only at runtime whether you're allowed to modify it. And you're only going to be allowed to modify it if you're the only thing that can modify it. So it's still exclusive. If you get this, if you call borrow mute and it succeeds, borrow mute is one of the methods on RefCell. If you call borrow mute on a RefCell and it succeeds, then you have an exclusive reference to the inside. You actually don't have an amper mute, you have a ref mute. I'll get into that. But this means that while you have this thing, no one else is modifying it. So you can still kind of reason about your code as though, you don't need to worry about everyone stepping on everything at the same time, right? And if you call borrow, that means that the thing inside the ref cell will not change while you hold this ref. You can think of that as having the same rules as amper, as just a shared reference. But what's going on here is that instead of having compile time proven that this is true, like the actual amper and amper mute do, there is bookkeeping being done in the RefCell type to make sure that if you called borrow, no one else has a ref mute. People can have multiple refs, but no one has a ref mute. And if you call borrow mute and you get a ref mute, if you get a ref, other people might have a ref, but not a ref mute, right? But that happens at runtime when you call borrow, right? If not, if that can't be true, if someone else has borrow muted it and you call borrow, you panic. Do you remember what panic means? Throw an exception, basically, except it's usually fatal. Exceptions can be caught in C++, that's kind of normal. Panics can be caught in Rust, but you really shouldn't. That's. Wait, what?
Wait, why shouldn't you catch it?
It's just, it's more just the convention. Panics are for errors that, like the only good time, I think, to catch a panic is if you just need to, like because you're dealing with pre-written code that's bad, or if you're writing a testing harness and you want to be able to continue doing stuff after a test panics. But like in actual code, you should use result for errors that you expect to deal with. Result is a different type. It's an enum with an OK and an error variant. It's different. The philosophy of Rust is just we don't unwind the stack a ton, but it is safe to do so. So it is totally fine. Like this doesn't become unsafe if it panics. The panicking is a safe thing to do. It's just that panicking is supposed to mean this is just a safe. Panicking in Rust is mostly used to to handle cases where your code has a bug that you've caught at runtime. It's not used to say something weird happened. It's used to say something wrong happened, right? So if you borrow and someone else has already borrow muted, currently has a ref mute, borrow will panic. So it's your job, the programmer, to make sure that never happens. But this allows you to reason about, this means that it's your job to reason about that as a static property of your code. And it's not the compiler's job. The compiler just enforces it, or the library actually just enforces it at runtime. And if
It just sounds unsafe to me.
What's unsafe about it?
I mean,
Yeah.
you're trying to access something that you don't have access to at runtime, and you have to manage that, and you're not really forced to.
Well, RefCell is not the default for a reason, so it's less safe. Safe means too many things is the problem.
That's true.
But it's not a good idea to jump for this, but this is fundamentally I think this is the best way that we've found, the rest of people have found, of modeling exactly what we're trying to do with the doubly linked list. And it doesn't even really have to do with, not having a garbage collector. Like RC fixes that problem, right? Or tries to solve that problem. Doesn't do it very well for a doubly linked list because there are cycles everywhere. But this allows you to write your code such that at any given point when you have the ability to mutate a node, no one else is mutating the node. And it does potentially cause panics, but if you write your code correctly, it won't cause panics. And the best thing about this is that the reason why this is actually safer than doing it the way that Java would do it is because in Java, you're not doing this bookkeeping. You're not making sure that you only have the ability to modify it when no one else does. So if you accidentally modify a node and an interleaved operation also modifies that node not from another thread, but from another, what's a good example? Just from another bit of code. If two pieces of code modify, what's the good way of putting it? I think the simplest case is really if you have an iter mute So the ability to mutate something through an iterator. No, now I'm trying to think. The tricky thing is in Java you just kind of don't think about this because in Java every reference allows you to mutate, right? But fundamentally, let's look at some of this code. I'm not expecting you to think it. Hang on. I don't know. So, yeah, honestly, this is kind of a bad example. The linked list. I'm gonna be honest.
We got OOP in Rust.
I don't know what you're trying to say. The issue that I have here is that what we're doing here with oldhead.borrowMute is we're saying borrow this mutably, and then but we're not storing it anywhere. So effectively, this is just this isn't really any semantically safer than Java in this particular case. But I think you could imagine a situation where, let's say you're writing a game, right? And you have two different, I'm not saying this is the right way to write a game. I'm just saying this is a way, right? You have two objects and two entities in the game, like two characters, non-player and player or whatever, and one of them attacks the other. You want to make sure that while you are attacking this other, while this character is attacking that other character, that other character can't modify the things, the fields of you, probably. I mean, you could say I want that to be able to happen, but what would be better, I think, is if you borrowed this character mutably while you're interacting with that other character, so that it can't borrow this character mutably again, because then you sort of end up in this like weird, like interacting with each other sort of thing, right? It's just sort of saving you from some issues, but it is only doing it at runtime. And in that case, if you had like ref mutes, the return value of bar mute, if you had those living longer than they are here, there may be an instance later in the thing where they do live longer. But if you had that, then ref mute really is getting you something relative to just doing it the Java way where every reference is mutable, right? If you screw up and they do try to modify you while you have yourself borrowed, then you get an error rather than just weird spooky action at a distance where like stuff happens that doesn't make any sense because two things are modifying one thing and that one thing should have had exclusive ability to modify itself. That's kind of abstract, but does that help somewhat? Yeah. So I just want to talk a little bit more about this. You might wonder, like okay, there are two big issues with RefCell. One is runtime cost. Anytime you call borrow, it does have to check, I think, a flag in RefCell. I actually haven't looked at the internal implementation of RefCell, but there's probably a flag in there that's like, am I borrowed mutably? There's probably like a flag that says, that has two different bits. Am I borrowed mutably and am I borrowed immutably, right? So if you borrow it, it's fine if it's already borrowed immutably, but if it's borrowed mutably, no, right? So it takes that runtime cost. And the other thing is it makes your API ugly, which is why in the end this safe deck layout actually is considered bad, and she doesn't do it better. It's just not really workable. It's basically impossible to hide the existence of these types inside your API, and no one wants to deal with these types. Everyone wants to deal with amper and amper mute. No one wants to deal with ref and ref mute. I think there are tricks for like taking a ref mute of a node and turning it into, or taking a ref mute of a struct and turning it into a ref mute of a field in that struct. So it's not like you can't do things that you might want to do, but it's just a pain. Does anyone have a theory as to why these types have to exist and we can't just use ampermute? Like, why can't borrow mute just return ampermute?
Doesn't keep the reference count.
So there's no reference count involved, but there are those flags, right? RefCell doesn't have a reference count.
Well, it doesn't keep like the flags for if it actually is borrowed.
Yeah. Actually, I'm completely wrong. There is a reference count in RefCell because you can have multiple borrows, but not or multiple refs. But it doesn't. Sorry, what was the thing you said? It doesn't keep the.
The other one doesn't keep like an actual like as correct check of like
What's
if people actually have these borrowed.
The amper
like
and ampermute?
Yeah.
This isn't about cross-thread, actually. RefCell is one of the things that is not not safe to share between threads. RefCell is not sync, which means amper of RefCell, because if you look at this, borrow mute takes amper self, which means I can call borrow mute even if I share the RefCell with others. Which is the entire point, right? We're punting the ability to determine if we have exclusive access to runtime. So the compile time thing has to think it's safe to share the RefCell, right? Otherwise, we can't even get into the case where borrow mute might fail because two people called borrow mute, right? Or someone called borrow mute when someone else was borrowing, right? Which is also a problem.
Oh wait.
Okay.
Does it just hang?
No, it doesn't hang. It panics.
Oh.
Because this is single-threaded. They're all in the same thread. There's nothing would happen if we just hung.
Yeah.
No one would relinquish it because this is just one thread of control. Which is actually the best way to understand RefCell is it's a single-threaded mutex. It only works on one thread because fundamentally, I think because the operations on that flag are not atomic. It's cheaper than a mutex because those things that keep track of how many people have borrowed me and how many people have borrowed me mutably, and should only ever be 1 or 0, are not atomic. Whereas in a mutex they have to be. And because it's single-threaded, it has to panic when it screws up because waiting would not do anything. Nothing would happen, right? But mutex also, no, it's not a version of a mutex. It's a version of a read-write lock. Has anyone not heard of a read-write lock? Read-write locks are great.
I haven't.
Okay, so mutexes, you just lock them or you don't, right? And one person has locked them at any given time, mutually exclusive, right? A read-write lock, you can lock for writing, in which case it's exclusive, or you can lock for reading, in which case it's not exclusive. But it's exactly the same rules as the borrow checker. And this makes total sense across threads. You know, Rust is really the key weirdness with Rust that I think gets a lot of people is that it takes lessons we've learned from multi-threaded programming and assumes that complicated single-threaded programs or single-threaded parts of programs tend towards being almost as complicated as multi-threaded programs. You don't have the awful hardware weirdness where it's like memory orderings, released, require, acquire, stuff like that. And you don't literally have the same kind of races. But if you're writing in a big code base, even if it's well organized, you'll still have weird spooky action at a distance, even if it's a single thread. So Rust actually, by default, constrains what you can do in a single-threaded environment using lessons from multi-threading. RefCell is a great example of that, because RefCell is a read-write lock, but on a single-threaded context. RefCell lets you have multiple people lock it for reading, that is, borrow it, or one person lock it for writing. Read-write locks exist in every language because they're just a good idea. It means you can have one thing that is often read and rarely written to and shared, and you still have parallelism between multiple readers, right? They can literally progress in parallel. Does that make sense? Because if you just had a mutex and the reading was more often, then they'd be handing off exclusive access to something where all they need is the ability to read it, right? Okay. I still haven't answered why this ref and this ref mute have to exist. Does anyone? I think Sam, you basically answered it. Ref and ref mute have to exist because if I call borrow onto RefCell, then like the RefCell would be kind of useless if, and let's put it this way, RefCell would be kind of useless if as soon as someone called borrow on it, no one could ever borrow it mutably, right? And if borrow just returned an amper, then nothing happens when you drop an amper. Nothing happens when you drop a shared reference. So there's no garbage collector in Rust.
Or you'll have to wait for the thing that checks the references, the reference count, and then gets rid of it.
Right, but how does it know the reference count went down? So when I borrow, I increment the reference count. When I borrow, I increment a reference count on RefCell that says I am borrowed once, right? Borrowed immutably once. But then when I drop, if this returned an amper, when I dropped it, dropping an amper does nothing. That's just one of the rules of the language because it's a built-in type, right? Same with dropping amper mute, actually. It's the same problem there. Dropping amper mute does nothing. So these exist entirely because they're implementations of drop. These, in addition to having a reference to the thing, I think they probably only have just one reference in total, but they have a reference to the internal thing, so you can access that. You can read it here, you could modify it here through this. But they also have the ability to, when they get dropped, tell the original RefCell, I'm not borrowing you again. Which is why we need a counter of the number of, or that's how we have a counter of the number of borrows, right? Because there need to be potential for multiple borrows of this same RefCell. And then we borrow it, and the counter goes up and up and up each time we borrow. And then as we drop them, it goes down and down and down. And then when it's 0, it's then again safe to borrow mute. And when we borrow it mutably, we set the flag that says I'm borrowed mutably. All borrows will fail until the ref mute is dropped, which says you're no longer borrowed mutably to the original RefCell, right? Does that make sense? Okay. So that's basically all I wanted to explain about this. This code is actually, there's nothing particularly Rust-ish about this code, except for what I just explained. So, I mean, it's just a doubly linked list, which is a pain. I like this comment of hers. In the process, we'll become familiar with interior mutability. I haven't said those words. Interior mutability is just the term for something inside this thing is mutable even if you have a shared reference to it. So RC has interior mutability, but you can kind of ignore it because that interior mutability is all about the reference count. That's the only thing that can change inside behind a shared, or behind multiple things pointing to the same thing. In RC, it's not behind a shared reference, it's between multiple RCs. Or it's behind multiple RCs. But RefCell has interior mutability that you actually do need to care about. You have an amper RefCell, but that doesn't mean the thing inside the RefCell didn't change. It just means that it doesn't really mean anything in particular about the thing inside the RefCell. All it means is that you can call borrow and borrow mute on this thing. Then when you have borrow mute, it no longer has, like the thing you have no longer exhibits interior mutability because the thing cannot change while you're mutably borrowing it. It cannot change aside from you. And when you call borrow, it no longer has interior mutability because nothing can change about it, right? But it has interior mutability between calls to borrow and borrow mute. Like if you drop the ref, right, or you drop your ref mute, then it could change out from under you. I think that it's a confusing term because they contrast interior mutability with either exterior mutability or inherited mutability, which is the default way Rust handles mutability. The example for this is just that if you look at this, we have a pubstruct list. We never say whether head is mutable or not. But that's because fields don't declare their mutability in Rust. Fields do declare their mutability in most other languages. You can have a const field in C++, you can have a final field in Java, right? In Rust, it's inherited or exterior because whether this is modifiable if and only if the list that I have is declared as mutable. If I can declare something as mutable when I do let something, right? I can do let mut L equals a list, or let L equals a list. And if I did let L equals a list, then the head inside is immutable. Interior mutability is by contrast with that notion that you inherit something from your containing struct, or its exterior that determines what's mutable, because now it's a property of the type itself. Like the type RefCell means that the thing within it can change. Does that make sense? Yeah, it's a mess. There's more types. There's cell.
It's a little
Yeah.
implicit, like,
What feels implicit?
the inheritance of like the
Mutability.
mutability.
Yeah.
I feel like if it was like explicit.
Like if I could say this is mutable or this is not mutable. Yeah.
Like I feel like that would have been more clear.
It makes sense. I kind of agree. I think what's nice about this, actually, well, there are two ways of thinking of it. One is there's the fact that we have inherited mutability by default is good in one way, which is that Java and basically every other language that doesn't determine the mutability of your fields based on the mutability of the outer thing, right? If I have a final list in Java, that means that I can't I can't change the identity of that list. I can't put a different list. I can't reference a different list from that thing, right? But the list determines entirely whether the list is mutable, right? If list is a mutable type, a final list can still change internally, right? In Rust, that's not true. I like that because it means that we just have to write one list type, and then we can use it either when we need an immutable list or a mutable list. Now, because Rust is not garbage collected, it's trickier to do that, but that's nice. I do still wish that there were a way to internally declare something as not mutable, even within mutable instances of this thing. Yeah, I'd like that. I'd like to be able to have final fields. You can't do that in Rust.
Yeah.
The way you're supposed to do that is just make it so that basically you just have to enforce that yourself. But it's not as bad as that sounds because you do have the module system. So you can make it a private field and then enforce it within the module, enforce it within that file that you never modify it, right? And then outside of that file, no one can even see it. No one can touch it.
You mean like a getter?
You can give it a getter. Yeah, you would make it private and give it a getter.
Setter.
And no setter. Yeah. But it's not my favorite. Swift actually does. In Swift, structs are a lot like Rust structs in that if you have a constant value of a struct, then everything within the struct is constant, right? I don't know how C# does. C# does weird shit, but C# has a similar thing. But Swift does allow you to still, even on a struct, declare fields as constant, such that no one can modify them. So even when you could otherwise modify parts of the struct, so Swift does kind of what you want. I just want to finish by mentioning two things. I'm sorry, I kind of wish I'd gotten to some code, but this code is just not interesting. And you can't, the place where it falls over is in this iteration section. Because you can't hide ref and ref mute, you have to be handing them to people. Your iter can't return an amper, it has to return a ref, so it's just a disaster. It's just annoying. You have to compromise. When it gets to unsafe, the one thing I want to mention is Miri. Miri is a slow and somewhat limited, but really exhaustive interpreter for unsafe Rust that ensures at runtime, as you run it, that your unsafe Rust code that boils down to the same sort of stuff that C does, right? But when you're interpreting it, it makes sure that you follow all of the rules of Rust.
Is it just like a UV sanitizer, basically?
It's a UB-SAN and an ASAN and one.
Oh.
And it's better than both, except it's an interpreter, so if your program interacts heavily with the operating system or the outside world, it might not work well under Miri, because Miri will try to simulate those things. But Miri gives you way more information than ASAN and UB-SAN. Like, UB-SAN will catch things that are simple, like overflows, right, just fine. Miri will do that too, but Miri will catch like weird a lot of it is we need Miri because Rust's rules for what you can do with pointers are actually way more complicated than C and C++. But the last thing I want to mention is just I feel like I should because of Apple, all that. So many of these concepts do carry over to Swift.
Yes, because of LLVM backend. Right?
No, not because of that. Because they share DNA. Because Chris Latner, well, no, he wasn't involved with both. But because they've been developed very similarly. The general rule of thumb is that if Rust does something at compile time, Swift does it at runtime. In Swift, most things are inside a RefCell implicitly. It's kind of a mess, at least to some extent. And all things of class type are behind an arc. But they do fancy optimization to actually figure out if things are ever shared between threads. And they remove the atomicity if it's not necessary. The other thing is that the type keyword, just another subpart of that, the type keyword in Rust is like overloaded. At the external, it's just like a synonym. And now you can talk about this type with a different name, like type link equals option box node or whatever, right? But in a trait, it's what's called an associated type, which means it's like a type that is associated with this trait, like the type that you return from an iterator. Swift has two different keywords. It has type alias for the alias one and associated type for the associated type one. So there's just shared stuff. What? Huh?
Can you complicate generic shit with the type thing in Rust? It's not just an alias, right?
Yeah, no. That's associated type. It's just an alias at the top level.
Oh,
at the top level of a file.
You can't do like type ASDF generic over some T and A equals something something.
Oh no, you could do that, but that's basically an alias.
But then you could do like const generics and stuff too, and then it gets like.
No, that's true. But it's still kind of an alias. It's not that you can't do very much fancy, but the fancy generic stuff is all when you have type within trait. Right. Or type within input. Anyway, sorry. Thank you for staying. I hope that was a lot of information, but I hope it was somewhat interesting. I really recommend the rest of this stuff, especially the stuff about Miri, because it's really cool.